Okay, so yeah, as I said, I'll be talking about joint work in progress with Martha Precup and John Shareshian. And so I will start. So a lot, like a big part of the talk is really gonna be motivating the objects that I will be talking about. So I'm not really assuming that you do research on Schubert or Hessenberg varieties. Okay, so to start, oh, let me see. Ah, good. Okay, so to start, let me describe the space where they live in. So I'm gonna be talking about subvarieties of the flag variety. So the flag variety is an important object in combinatorics and representation theory, and it's just lists or sequences of vector spaces. So you want n vector spaces, and you want them to be organized into an ascending chain. Okay, and it should be complete. So, oh, oops, sorry about that. And it should be complete. And so for an example of a point inside your Schubert variety, it's just very simple. You can take something like E1, comma, E1, comma, E1 plus E3, and then C3. This is an element in F3. And yes, so this is the ambient space of what we will be talking about today. Okay. So one important thing when people talk about flag varieties, one very useful aspect about them, one of the reasons they appear in so many different fields, is because they behave very nicely with respect to groups or group actions and things like that. So a very important observation that doesn't seem to advance at this point is that you can represent the elements of the flag variety as invertible n by n matrices, where you let n, so given a matrix M, you're gonna organize it into, like it corresponds to, or not corresponds, but it gives rise to the following flag, where you just take the span of the first column, then the span of this first and second column, and so on. And so with that in mind, if we looked at our example, then the matrix that we would have here would be like 1, 0, 0, 1, 0, 1, and then here it can be anything. So maybe I'll make it 0, 1, 0. So this is one way in which you can represent the elements of your flag manifold by invertible and by n matrices. And maybe it's not fair for me to do the backwards line, so let me erase it. And so I erased this, that it came back again, but I want to erase this going backwards, because notice that if you have two different invertible matrices, then they might represent the same flag, right? We know that the column span of a matrix doesn't characterize it. So, but we can exactly say when two matrices represent the same flag, they represent the same flag if and only if there's an invertible upper triangular matrix B, such that when you multiply on the right by B, you go from one to the other. And this roughly amounts to doing column operations, where like you need to leave the first one fixed, but then you can add the first column to the second column to change your second column, and then you can add the first two columns to the third column to change it, and so on. So this is roughly what is happening. And with that description in mind, then we have that, okay, so if we let our group be the special linear group, and we let B be the subgroup of upper triangular matrices in G, then we can describe the flag manifold. Oops. The flag manifold is going to be G mod B. So we can think of the elements of the flag manifold or the flag variety as cosets. And of course, okay, I'm calling it variety, and I'm not going to go too deep into why it's a variety. Here I'm describing it as a set. But you can embed it into, in case you're wondering why I have the word variety there, you can embed the flag, this space, into a product of projective spaces. So if you're familiar with the Grassmannian is a variety, and you make it a variety by embedding it via the Plucker embedding, where you use like determinants to encode a dependence. And here it's the same idea. So you can use determinants to encode like that the first vector space is contained in the second one, that can totally be described in terms of determinants, and thus it can be described in terms of Plucker coordinates, and similarly to the Grassmannian, you can embed it into a product of projective spaces with equations. So that's the variety structure of it. But it will be, for us today, this is good enough. Okay, we will definitely be using this posted description, not so much the variety description. Okay, so next what we want to do is we want to talk about which, oh, sorry. Okay, so we want to talk about the Bruhat stratification of my flag map or my flag variety. So this is the flag variety plays a central role in combinatorics, representation theory, and algebraic geometry. And one of the reasons is because of this Bruhat stratification. So we're gonna, to describe it, let me start by considering another subgroup of the special linear group. So I'm gonna take n by n diagonal matrices that are invertible in SLN. And we have a torus action of these diagonal matrices in your flag variety. And it's just, so remember, I described the flag variety as cosets, and the way my diagonal matrix acts on my coset is just by matrix multiplication. So you just take the coset of T times T. And I will emphasize, okay, so I call this T is an algebraic torus. So it's the isomorphic to C star to the N. And a good spirit behind when those combinatorics arise, it often happens when you have a torus action. So if you have a torus action like we have here, you can often think about different objects associated to it. One of them is the torus fixed points, and you can encounter combinatorics that way. So the permutations of n, where just to be very clear, this set n is just, this is standard in combinatorics, but just in case I want to be very clear that this is just the set of 1 up to n. So if you take the permutations of n elements, they're going to be in one-to-one correspondence with the torus fixed points of your flag variety, meaning like the points in your flag variety that do not get moved when you act by T. And the way you can make it correspond is, well, if you have your permutation, you can send this to the following flag. So it's going to be E of W1, E of W1, comma, E of W2, etc. Okay, so you just list, like, in terms of matrices, this is going to be the permutation matrix of your W. So you get the first span of your first column of your permutation matrix, and so on and so on. Okay. And similarly, we also have this description in terms of cosets of the flag variety. It's very nice. It helps us talk about group actions on the flag variety very straightforwardly. We just did that with the torus, but we can also do that with B, which I will refer to as the Royal subgroup. So remember that B are the upper triangular matrices, and B acts on the flag variety again by matrix multiplication. So if you have the coset of G and you want to act it by an element of or an upper triangular matrix, then you just multiply the matrices B and G and you see what flag they give. And the theorem that one of the reasons this action is very nice is because you can then stratify your flag variety as a disjoint union of certain orbits. So here, this BFW is an orbit. It's a B orbit, or the B orbit of the flag that I have, of the flag of the permutation. And so this stratification is quite important. And so I wanna, there's names associated to the strata that I have over here. So first we have the Schubert cells. So these orbits are called the Schubert cells. And then the Schubert varieties, that is the first subject I wanted to talk about today, are gonna be the closures of those Schubert cells. And so one of the ways you can do this closure is just by taking limit points, or maybe so maybe that's one way, or maybe like finding all the equations that vanish on your Schubert cell and adding all the points that vanish on that Schubert cell. That's another way you could also do it. But let me tell you, because the theme of today is that Schubert varieties are combinatorial. That's going to be the initial theme. So you can really close Schubert cells in a combinatorial way. Okay, so what we have is that, so we actually have that, in fact, you can close your Schubert cell by taking a disjoint union of Schubert cells. So we have that the Schubert variety associated to W is a disjoint union of Schubert cells where, well, which ones there is, they're gonna be given by some partial order called the Bruhat order. So the Bruhat order is some order that we associate to permutations. And let me be very, very concrete on about what it is. And there's so many definitions, but I like this one. I think it's concrete. So we will say that V, two permutations. A permutation V is less than or equal than permutation W if for all I comma j in N. Well, when you look at the permutation matrix of V and you take this bottom left corner and you count the number of ones in that permutation matrix, there should be less than or equal than if you repeat the exact same process with W. So for example, the one that I have down here, we have that 3, 1, 2, 4 is less than or equal than 4, 3, 1, 2, because, well, I won't do it all, but notice that I really should use a different color. So let me pick this one. So notice that if we start like filling in, like if we look at this part, we get a 0, whereas here we have a 1. So the number of ones is less than or equal to, that's still satisfied. Here you got 0, and here you have 1, and well, so on and so forth. So I won't do it all, but we can, like maybe you're really fast and you did it already. We see that indeed 3, 1, 2, 4 is less than or equal than 4, 3, 1, 2 in Bruhat order. So we describe like this Bruhat order allows us to close Schubert cells. So once we understand the Bruhat order, which is entirely combinatorial, we are able to close Schubert cells and thus define Schubert varieties. Okay. So as I was hinting at before, Schubert varieties are combinatorial. We already saw one instance of that. To define them, to take the closure of Schubert cells, we just do combinatorics. But here is another nice instance of that combinatorics arising in Schubert varieties. We have that the dimension of a Schubert variety is equal to the number of inversions of that. So in case you're not familiar with that, it's just the number of pairs of numbers that are in this order. So it's the number of I comma j's such that I is less than j and W of I is bigger than W of j. And in general, I won't really, like, we will see a couple of instances of it, but in general, there is this beautiful dictionary between combinatorics of permutations and geometry of Schubert varieties. So the other combinatorial aspect of Schubert varieties that I want to concentrate on is a pattern avoidance, because this is one of them. It's a classical result and it's very nice. So we will say that a permutation B avoids another permutation, but I'll only do it for a concrete permutation, avoids the permutation 4, 2, 3, 1. If you cannot find 4 indices that have the same relative order as 4, 2, 3, 1. So in other words, that satisfy this relation. So for example, let's to see pattern avoidance. If we look at 7, 6, 5, or 3, 2, 1, I think that one's easy to see that it avoids 4, 2, 3, 1, because like if you restrict to 24, well, 20 subsequence of 7, 6, 5, 4, 3, 2, 1, it's always going to be largest, then second largest, third largest, and smallest. It will never be like largest, then second smallest, then second largest, and smallest. You'll never have it. So this is this permutation is easy to see that it avoids 4, 2, 3. And conversely, if a permutation doesn't avoid a pattern, then we say it contains it. So this permutation 7, 4, 3, or whatever we have there, if we look at it, notice that we have this subsequence 7, 3, 5, 1. And that subsequence is in the relative order 4, 2, 3, 1, right? Largest, second smallest, etc. So it contains this permutation. And similarly, you can define pattern avoidance for any 2 permutations, but today we will only care about 2. And similarly, we will say that B avoids this permutation if you cannot find 4 indices such that they have the same relative order as 3, 4, 1. So analogous definition. And there's this, as I said before, this classical result by Lakshmibai and Sandhya, which they classified which Schubert varieties are smooth. So you have that a Schubert variety is smooth if and only if W avoids those two patterns. So again, geometry of Schubert varieties is being described in terms of combinatorics. And then they just to like give a little bit of a sense of in what other way Schubert varieties are combinatorial and what way they play a central role. I'll tell you briefly about a difficult problem in combinatorics. So one corollary of the Bruhat decomposition, so remember that was, we said that the Bruhat decomposition said that your flag is the disjoint union of the Schubert cells. And one corollary is that the classes of your Schubert varieties form a basis for the cohomology ring of your flag variety, an immediate consequence. And now this cohomology ring of the flag variety is combinatorial, and in particular, Borel gave a presentation for that cohomology ring, described it as the quotient of a polynomial ring by the elementary symmetric functions that I'm not really going to define. So, but there are some symmetric functions that are fundamental in algebraic combinatorics. And within this, maybe I should have done it the other way around, but anyways, we have that under this isomorphism, you have that the Schubert polynomials inside this ring are gonna correspond to Schubert varieties. And I'm not defining Schubert polynomials, but they're very combinatorial. You can just define it in terms of your permutation. And so one classical, very difficult problem in algebraic combinatorics is the following. So I'm telling you that Schubert polynomials or these classes can be described just in terms of permutations. And well, since the Schubert classes of the Schubert polynomials form a basis for the cohomology ring, then you know that when you multiply 2, you can expand it as a sum with some coefficients. Okay, so this is the expansion of the product of two Schubert or two classes of Schubert varieties using the basis. And it is known that each of those coefficients are greater than or equal to 0 in some sense. Like one of the ways it is known is because what is that coefficient? You can think of it as counting transverse or a number of points in transverse intersections of 3 Schubert varieties. And so I don't want to go into too many details about what that is, but from what I told you, it's counting number of points, and thus it has to be greater than or equal to 0. So it's geometrically, it makes sense that it's greater than or equal to 0. And lots of mathematicians are very interested in giving a combinatorial rule that computes those coefficients. And lots, well, there has been partial progress. There's really, yeah, it's a difficult question, but it's an important question in the field of algebraic combinatorics. So hopefully here I convinced you that Schubert varieties are indeed combinatorial and they play a central role in algebraic combinatorics. Okay, good. Okay, so let me do one thing. Okay. So next, we're gonna go ahead and talk about Hesenberg brushes. And I suspect you're probably less familiar with them, but we're gonna talk about them in twice. First, we're gonna talk about them in the original definition. So we're gonna talk about the Hesenberg varieties that were defined by Demari and Schliemann. And the input, there's different input that we can take, but for today, I'm gonna just take as input what is called a Hesenberg function. So a Hesenberg function is a non-decreasing function from n to n, such that h of I is greater than or equal to I for all I. And so to define a Hesenberg variety, that's one of the inputs. And the second input is gonna be an element of the Lie algebra of SLN. So the Lie algebra of SLN consists of the n by n matrices X, such that their trace is 0. Okay. So as I mentioned, if you give me a Hesenberg function and an element of your Lie algebra, then you can construct a Hesenberg variety. And then your Hesenberg variety is just going to be the elements in your flag variety, such that when you act on your for the image, the image under X of the I yes, element of your flag is gonna be containing the HI element of your flag for all I. Okay, so this one, I mean, yeah, one has to do examples to understand what it is, but at least in terms of the equation, I think it's clear what it is on that. And so let's look at some examples, and the examples, one is gonna be very concrete, and then the other two, you'll just have to trust me. So one is to maybe get a better sense of what they are, and the other two is to motivate. So let's suppose that HI is a constant function n, or the element of your Lie algebra is 0. So in any of those cases, you'll notice that this condition is satisfied vacuously. So they're really not imposing any conditions. So in those cases, you have that your flag, that your Hesenberg variety is equal to the flag. Okay. And then as promised, like, so the theme of what I'll tell you next, starting now, is that Hesenberg varieties are also combinatorial. So let me give you a second example that starts heading us towards that direction. So let's suppose we have this other Hesenberg function. So it increases your index by 1 for almost all of them except the last one. And I guess I deleted something. And then we suppose that you have a generic element, so a generic matrix, meaning you just pick the entries random. So if you're in that case, you will have that the Hesenberg variety is the toric variety associated to the Bray arrangement. Or in other words, the toric variety of the permutation. Okay. So we encountered this beautiful toric variety for some special instances of Hesenberg varieties. And then the third example, and I won't dwell into it too much, but if you're familiar with these objects, this should excite you, that if you choose X and H appropriately, you will obtain the Springer fiber and the Peterson variety, like different choices, obviously. But these are some important objects in representation theory. So again, these Hesenberg varieties, it can be very different. They encompass different types of objects, and at least, well, I'll convince you even more, but at least for now, we start seeing that they're combinatorially nice. But much less is known about them. So they are combinatorial, but much less is known. So remember, one of the things I told you about Schubert varieties is their dimension. So we can classify the dimension of a Schubert variety by looking at the length of a permutation or the number of transpositions. Here, knowing the dimension of a Hesenberg variety is very hard. Smoothness, I also told you about smoothness, like classifying which ones are smooth can be hard, or knowing how, like if it's not smooth, it contains singularities, how bad can those singularities be? That's also a difficult question. So like there's lots of things you might try to ask, like in some sense, it seems like I'm gonna translate the story of Schubert varieties into Hesenberg varieties, but that's not always possible. Like having torus actions can be really hard, knowing which torus fixed points are there, all of that is very difficult. However, some things are known. So my co-author and colleague Martha Precup showed that although Hesenberg varieties are not smooth in general, they often have palindromic pointer polynomials. So that's a very nice fact. And the next thing that I want to mention, I'll spend some time motivating them, is that while studying the cohomology rings of Hesenberg varieties leads to interesting combinatorics. So there's this big area of research that is interested in understanding the cohomology rings of Hesenberg varieties. And one of the motivations to do so is that there's many authors that worked on this, including my co-authors, Martha and John, that when you pick a generic element of your Lie algebra, the cohomology ring of your Hesenberg variety is related to the Stanley-Stanbridge conjecture on chromatic symmetric functions. So just to tell you a little bit about it, I won't spend too much time on it, but let's suppose you start with a simple graph with n vertices. So then there's a symmetric function associated to this graph, and the way you define it, it's the chromatic symmetric function, is gonna be this sum. So you sum over all proper colorings, and you multiply the variables for the colors that appear in your proper coloring. And it's a generalization of the classical chromatic polynomial, because if you substitute 1, 1, 1, 1, you will just get the classical chromatic polynomial. Okay. And well, the Stanley-Stanbridge conjecture is not really, it's not really concerning all possible graphs. It's restricting to a certain family of graphs. So if you give me a Hesenberg function, and you can construct a graph associated to the Hesenberg function where the number of vertices is n, and you have edges whenever I is less than j, and j is less than or equal than h of I. So like you have, for this particular Hesenberg function, 3, 3, 4, 4, you can construct, you can construct your graph. It has 4 vertices, and you always have that I is connected with I plus 1. And then in this case, you also add this extra edge. So this is gonna be the graph associated. And so the conjecture is gonna be that the chromatic symmetric function associated to your Hesenberg, or associated to this graph, which is associated to a Hesenberg function, is E positive. So this goes back, this ties a little bit to what I told you about the Schubert problem, that basically what it says is like, so the elementary symmetric functions, which arose when I was talking about the cohomology ring of the flat variety, they form a they form a basis for the symmetric polynomials. And there's lots of questions in algebraic combinatorics of like, oh, when you have a symmetric function and you write it in terms of a basis, are the coefficients positive or not? And then the follow-up question is like, why are they positive? What are they counted by? And things like that. So this is a question in that realm where we're looking at whether expanding, well, I'm not, but the experts are, whether expanding the chromatic symmetric function into the elementary symmetric polynomials is positive or not. So hopefully I've convinced you that both are combinatorial. So next I want to go ahead and talk about the actual question that I have, and that Martha and John and I addressed. So here, one of the things I wanna say is like, so there's this question, I want to talk about why this question is natural. So the first reason this question is natural, well, is because they both live in the flat variety and they're both combinatorial. So that's one reason one can ask, like, how are these two families or varieties related? But I will also say that another reason it is interesting and important to ask this question is because, well, Hesenberg varieties, there's like the tools to study them often come from intersecting them with Schubert varieties, like knowing what the intersection of a Hesenberg variety with a Schubert variety is. So and that requires understanding the relationship between the two very well if you want to understand the intersection. So this is a natural question because, well, there's a lot of overlap, like in the techniques to study both. So Juliana Timochko asked this question during a Banff conference a few years ago. And well, there's many ways to interpret this question. So maybe from the setup that I've given so far, I can already answer this for you. So then the answer already is gonna be no, just given the setup that I have given. So let's pick this permutation, 4, 2, 3, 1. that it actually arose before vanity. So we have this permutation 4231, and like I won't go through all the details, but if you like, this is a fact that no matter what X and H you pick, no matter if your Hesenberg variety contains this Schubert variety, and well, okay, you need something. You need that X is non-zero so that your Hesenberg variety is not on the nose, the whole flat variety. We're able to show that the Hesenberg function has to be the constant function 4444. And I don't know if you remember, but that was our example 1. In our example 1, we showed that from this, it follows that the Hesenberg is the whole flat variety. So this already tells you that there is no way that a Hesenberg variety can be equal to this Schubert variety. Okay. So, but then we got interested in like whenever you encounter, like after having this example, we like it's natural to think about pattern avoidance, because remember that theorem I told you about smooth Schubert varieties. So this is one of the patterns that you want to avoid for a variety, for a Schubert variety to be smooth. So with John and Martha, what we proved is that if there exists an element of your Lie algebra and a Hesenberg function such that xw is equal, well, let me just write it better. So, such that your Schubert variety is equal to this Hesenberg variety, then you must avoid that pattern. Okay. So we like there's no way that you can have a Hesenberg, like this is a nice instance of our pattern avoidance. And an immediate consequence of our result is the following. So we're applying the Marcus-Tartos theorem, that is also known as the Stanley-Wilf conjecture, which says that the number of permutations, well, it's a consequence of this, because since we need to avoid this permutation, then the number of Schubert varieties that are Hesenberg varieties has to be bounded above by an exponential function. Okay. And well, we also wondered, like, what about the converse? Or like, what can we say about pattern avoidance? So first, I want to emphasize that the converse of our theorem does not hold. Okay. So we were able to completely classify for n equals 4 which Schubert varieties are Hesenberg varieties. So for n equals 4, you have that we have that the Schubert varieties that are Hesenberg varieties are exactly oh wait, is not. Yeah, I should have said is not. Is not. The ones that are not a Hesenberg variety are varieties are exactly this. Okay. So that tells us that the converse of our theorem is not going to hold. Now we don't have a complete classification for n equals 5, and I would say that we don't believe that pattern avoidance is going to be the way to classify which Schubert varieties are Hesenberg varieties. But it is very nice that we're able to find one pattern for which it doesn't, like that already tells us there's no hope.
So do you have the same theorem for the 2314 pattern?
No, we do not.
Okay.
So yeah, that's a good question, and maybe yeah. Yeah, I forget right now what would an example be, but yeah, there are non-smooth Schubert varieties that are Hesenberg varieties. Yeah, and okay. Yeah, that's yeah, because we do have it. Yeah.
Just a quick question about this about the number, and do you have like a do you actually is the exponential a right bound, or is there anything like maybe like a polynomial, maybe it's actually polynomial, something like that, like a matching lower bound maybe?
Yeah, that's a good question. So we do not know, because we do not know all the permutations that have to be avoided. So yeah, it would be nice if we could bring it down to polynomial, or maybe show that it is not, but yeah, we do not know at the moment. This is the best we can do at the moment. Okay, so now I'll go to more general varieties, because like Hesenberg varieties come in many different flavors. And of course, one natural way to extend the definition would be to other types, and we will talk about that briefly. But I want to extend it to a very general setting. So Goreski, Kotwitz, and McPherson defined Hesenberg varieties for a more general setup, even in type 8. So we're gonna start with the input is gonna be, you're gonna start with a representation. So you have a representation of SLN, and you pick a V invariant vector subspace of V, of your representation, and you pick a point in V. And using that as your input, you will get an associated Hessenberg variety, which is gonna consist, and so I'm using this notation, is gonna consist of the flags such that this equation holds. And so bringing back to our original definition, so this looks very different from what I told you before, because what I told you before, it was something like X Vi containing V of Hi. This was like the main condition. But it does agree. It does agree with this definition, mainly if you take, so you want to take Phi to be the adjoint representation, which in other words means that you take your vector space to be the Lie algebra, and you take the adjoint representation acts as follows. Okay. And then the last part that will make things agree with each other, not that I'm going to prove to you that the two definitions agree, but you have that subspaces of your Lie algebra, you can describe them in terms of the Hesenberg functions by, or V invariant subspaces of V, you can describe via Hesenberg functions by basically, like, you can graph, like, let's do one very concrete example. Let me suppose that H is going to be kind of like 1, 3, 3, 4, or something like that. So what you can do is we're in the setup of a 4x4 matrix, and you will just maybe like, let me draw the picture and I'll tell you what's going on. So I just highlighted the one, like one row, then I highlight 3 rows, and then 3 rows, and then 4 rows. And that's like, so this is how I get this picture from this H. And then the subspace is basically going to be matrices in SLN where they have to be 0 at every entry that I did not highlight. And fact for today, yes, if you do this conversion, you have that the two definitions agree. So this is a much more general setting for Hesenberg varieties. And I will emphasize that, of course, they're still combinatorial, because the previous ones were combinatorial. This also are going to be combinatorial, but even less is known. So at this setting, there's very few instances of the literature studying this very, very general setting. The setting where most people care about is in the adjoint representation, which was the previous setting that I told you. And here, there's not that many tools to study them. So everything that I told you before holds. Which ones are smooth? What are their dimensions? What is their singularities? Lots of things to ask for this very general Hesenberg varieties. So our theorem is going to be as follows. In this case, when we go to this very general setting, is that every Schubert variety and here I'll put it in parentheses, but this holds for any lead type. And if I wanted to do it for any lead type, I should replace this SLN by its corresponding lead group. But in any case, so any lead type is a Hesenberg variety of this form. Okay. So for this very general Hesenberg varieties, we obtain all Schuberts. And let me tell you a little bit about the details of our theorem. So the details, just not that I'll go through the proofing in much, but I do want to emphasize one thing, so or a couple of things. So a single representation and vector works. So we're gonna, so if you are familiar with representation theory, you have that like some representations correspond to weights. So if you have a strictly dominant weight, so for example, we're gonna have lambda to be n minus 1, n minus 2, all the way to 1, 0. If we have this weight, then there's an irreducible representation associated to this weight, and it's the one that has highest weight lambda. So we're gonna let this single representation will be good enough for us to realize all Schubert varieties as Hesenberg varieties. And the vector, like once we're in this setting in representation theory, like your best guess is probably going to be why don't we just take x to be the highest weight vector of this representation? And yes, that will also work. So this is the representation and vector that works for all. And of course, what varies is going to be h. So how do we choose our h? In order to choose our h, what we do is, so given an h is going to depend on w, of course. So if we have a permutation, we're going to define h sub w to be what is called the Denominator Module. And if you're not familiar with that, well, because I'll give you or if you're familiar with it, maybe I'm giving you a different description. But what it is you just take, okay, so let's go inside to out. So you just take your highest weight vector and you act on it by, oh, so here, let me emphasize, this is the permutation matrix. Because I did not define that notation, the permutation matrix of W inverse. And so what you do is you use your representation to act on your highest weight by these objects where you run over all elements of your realm, and then you take the C-span of those vectors. And that's going to be your H sub W. And then the fact is that, I don't think I wrote that down, I did, that X sub W is going to be the Hesenberg of B lambda comma H W. And now, like, once we realize, like I would emphasize that the core of our proof is actually kind of hidden in Denominator modules, because Denominator modules have a nice property that you're able to talk about lying inside your inside of this space using Bruhat, like if you want to know which, like when is a permutation is B inside your Denominator module, you can use the Bruhat order to know what that is. And from what I told you about Schubert varieties, the Bruhat order is basically what you need to understand. So the Denominator module and facts that are known about the Denominator module make this work very nicely. The Denominator module behaves extremely nicely with respect to Bruhat. But yeah, so that is all I have to say, I think. Yeah, no, that is all I have to say. So thank you.